Hello. Can you guys hear me?
Yes, sir.
Okay. Yeah, today there might be a lot of technical issues. You might suddenly lose me because it's almost the first time I'm teaching offline in some form. Okay, so yeah, as I told you, please let me know what your doubts, questions. Anybody from online, offline?
Gave us something to think about.
Yes.
So
yes, I gave you these things to think of, right? So you have yeah, so you have a graph G. By the way, the people in online, can you see the board properly?
Yes, sir.
So graph G, and your goal is to find a vertex cover, right? Which is basically, so vertex cover V prime subset of V such that for all edge UV in the edge set, E intersection or UV intersection V prime is non-empty. Okay, so the vertex cover problem says that find the smallest vertex cover. Cover of G, and instead we ask for something like an approximate cover. So your job is to find a vertex cover V prime such that V prime is less than, say, 2 times the minimum vertex cover. So how do you go about it? Yeah, I mean coordinate, yeah. How do you go about it?
I was thinking of some greedy approach.
You're thinking of some greedy approach. So what is the greedy approach?
So we start with some vertex and we just see all the neighbors.
Okay.
And mark them in some way.
Right. So you're taking a vertex, look at all the neighbors that are already covered,
and
remove them, take the next one, go ahead. Very good. So greedy approach will indeed give me a vertex cover. That is no doubt about that, right? So greedy approach, it will give me a vertex cover, okay? So will output a vertex cover. But the main problem is how bad is the output? Can the output be really bad?
I was unable to prove it, but I think that it would be bigger than should satisfy the condition.
Yeah. So think of this one, okay? A graph like this, a star graph. What is the vertex cover of this?
So the vertex cover is just the one vertex.
There's a single vertex, right?
Yes, sir.
But instead, if you do the greedy approach and take this vertex to begin with,
yes, sir.
then you will remove this vertex.
Yes. Then.
And then you are picking up the whole vertex after that.
So we have to.
So okay, so greedy approach does not give you any guarantee that you are coming anywhere close to the best. So any other approach? Last time somebody, who was it?
I said that, so I thought of something like a matching. So
you sort of something like a matching. I mean, why did you think of something like a matching?
Because if we have if we have perfect matching, then we can just choose the one of the vertex from each.
Matching.
Yeah.
Oh, excellent. So if you have a perfect matching, you are saying that you can choose one of the vertex from each pair
Yes.
and be done with.
Yes, sir.
Sir, that's not necessary, right? Because what if we have something like three edges in one line,
Yeah,
and we choose the perfect matching would be the first edge and the third edge, right?
right. You're completely right. So you have a graph like this. Okay. So this is a perfect matching.
Right.
So I am choosing this vertex and this vertex. I'm choosing one from.
Yes, sir.
I mean that this is a matching. This is a matching. I mean I'm taking one from each matching, but
Yeah, that is not a cover.
that is not a cover. But you're not too far. Can you think in this direction? Why did you even have this intuition about something like this can happen? Why is it that you thought, okay, take one vertex from match? See, this is where I think you have to think a little bit in a different way. Your job is not to come up with the best matching, the best vertex cover. Your job is to come up with a vertex cover that is just constant away,
Okay.
constant multiple away.
So basically, we want a matching, but I mean, we are using the matching approach, but we also wanted to satisfy the vertex cover conditions.
Something like that. So, okay, if I have a matching, if I have a perfect matching, okay, or if I have a matching of size M, can you say what is the vertex cover? Some upper bound, lower bound, something? Yeah, somebody was saying something here.
Sir, maybe we can have some sort of a maximal matching where we
Okay.
can just use a greedy approach to create a maximal matching. And
Mhm.
then we can just choose all the vertices covered by the edges that we selected.
Very good. So what happens? So you are saying that you are choosing one vertex per matching here, right? What happens if I choose both the vertex for matching? Okay, now you say, okay, then you are choosing the whole graph. Okay, of course, not very good. But don't think of the graph to be just having a perfect matching. What happens if I have a huge graph? Okay, and this is a maximal matching. What does it mean? That there are some vertices which are unmatched. Okay, but in these vertices there is no edge between them. Because if there is a vertex edge between these two and these two are not matched, I would have matched this to this and I've got a better matching, right? So this is not allowed. So a maximal matching. So in a graph, a maximal matching can be pretty low, right?
So like in the case of the star graph,
Yes,
the maximal matching is a single edge.
it's a single edge. In a star graph, the maximal matching is a single edge, right? So in this situation, what can we say? If we choose both the vertices that are part of some matching, the matched edge, then what happens? Both of them.
So we know that that is definitely a vertex cover because the unmatched vertices are making an independent set.
Right. So that's one way of thinking of it. Because the unmatched vertices don't have an edge between them, so they form an independent set. And like we saw it last time, the independent set, the opposite of an independent set, is a perfect, is a vertex cover. But the other way is just to prove it, right? So what does it mean that this vertex is, so it was maximal matching, meaning it doesn't have a edge to any of the other non-matched vertices. If at all there is an edge to already a matched vertex.
Yes.
But since I've already picked up all the matched vertices, So that means all the vertices will be covered.
Yeah.
Excellent. So that means if I give you a match, or if you find a maximal matching, right? In that case, so there exists a vertex cover of size less than 2 times the maximal matching. Now you will say, what is a maximal matching? Is there a well-defined one? No, it is not. Okay, it is not. But give me any maximal matching.
What do you mean by well-defined?
Meaning 2 maximal matchings might not have the same size.
Yes, sir.
So that's the thing, right? So and I'm not saying that maximal matching is a fixed quantity.
Yes, sir.
No.
We have defined like this.
Maximum, no, not a maximum, but a maximal.
Those are different.
For example, in this graph, I can have these 2. This is a maximal matching, right? And at the same time, if I had just picked this one, that is also a maximal matching. Okay. So in some sense, if you want to say, what you can say here is that there exists a vertex cover of size, since it is a less than 2 times the maximal matching, the minimal maximal matching. Right. Less than twice of the minimum of the maximal matches. Okay, that's good. But say I wanted to look at the minimum vertex cover. Can you know how can I talk about? So if I have a graph, let's go back to this whole thing. I have a matching. Somebody has given me a maximal matching. Okay. Again, something. Okay. What can you say about the vertex cover?
So it will definitely have to have at least the number of edges in the matching number of vertices, because all these edges are disjoint. So in order to cover all these edges, we need to at least pick one of the vertices.
Right.
In every single.
This is the matching. This is the matching. This is the matching. This is the matching edge, right? How do you cover a matching edge? Or how do you cover any edge? By taking either this one or this one. So that means out of this edge, one of these 2 has to be there. Similarly, out of this one of these 2 has to be there. Now, is this 2 and this 2 disjoint or not?
Yes.
This set.
The disjoint in
this vertex set.
Yeah.
Vertex set is disjoint. So that means if for every edge in the maximal matching, okay, at least one vertex has to be taken into the vertex cover. So that means a vertex cover, okay, any vertex cover is more than, or size of the vertex cover is more than the size of the maximal matching. And any maximal matching, right? Size of it is bigger than any maximal matching. So in that respect, we can say that it is the size of the maximum matching. Good. So that means I have this vertex cover. So for all vertex cover, or maybe I can also say that minimum vertex cover is more than maximum matching. Okay, great. Now from this 2, can you get anything? So you can produce a vertex cover of size 2 times the maximum matching, which means that this is less than 2 times the maximum matching, right? Maximum matching, which is less than
2 times the minimum.
2 times the minimum. So see what happened. Finding the minimum vertex cover was NP complete. There's no way we could, or almost no way we could prove a polytime algorithm. But as soon as we relaxed our condition of finding the minimum of them, instead we tried to find out a approximation of it, we're good enough.
So we restricted ourselves, and so this is the maximum matching we can find in polynomial.
That maximum matching you can find in polynomial time, but it doesn't matter whether maximum matching. All you have to do, see, look at the algorithm. Algorithm was from the maximal matching, right?
The maximum.
I mean, even maximum matching you can find in polynomial time. I don't think we have done this particular thing in class. Okay, but we will do it next week or something. But maximal matching, a very simple, stupid, greedy algorithm will give you a maximal matching. Right? Take a matching, remove all of them. Take another matching, remove all of them. Right? All of the adjoining adjacent edges. So maximal matching is very easy. Trivial. Right? So it's a linear time algorithm. So maximum, yeah.
So the problem of maximum matching, we're trying to be very careful as to what edges we choose. But here we actually want to reduce the number of edges in the maximal matching. So we can be as clumsy as we want, and it would actually be better.
We can be as clumsy as we want, and still we will have a 2 approximation.
So in fact, being more clumsy will be better for us because we'll get a lower vertex cover then, right?
No. Yeah, actually, in fact, you are right. Yeah. I mean, if we can manage to get lower the size of the maximal matching, it's better for us. Yeah, I mean, that's what we may become. Yeah. Yeah. Any question?
No, this session is being recorded, right?
This is being recorded. Yeah.
He's asking for the record.
Yeah. No, but you are here. I mean, I prefer you to ask questions.
No, actually, the thing is that I have forgotten some of the concepts of the thing. So
Okay. Okay, so anyway, so basically what I want to say here is the following, that finding the exact minimum vertex cover is NP complete, but finding this is what we call as a 2 approximation. Yeah, 2 approximation of vertex cover. I mean, I don't think I have to explain why these 2 concepts, right? 2 approximation is in polynomial time. So if I want to erase some of this stuff. Hey, by the way, for people who are not in class, do you see any difference between reading this writing and that writing? Hello? Aniket?
Yes, sir, there is a difference.
They are both same?
Sir, if you could increase the font size.
Okay, font size is fine, but
Yes,
otherwise
sir.
it's equal.
Yes, sir. Yes, sir.
so you can like it to comment.
It's like a composition. So okay, I will increase the font size. Yeah. Okay.
So
what? Yeah.
So the visibility on the top half of the board is better because of the lighting issue. On the lower side, it's a bit less visible, but it's still.
Yeah, that's exactly the opposite of what people in the class is saying, but I understand.
Oh, okay.
No, the lighting reflection to not a big question at all. Whatever. So we have this vertex cover is NP complete. Right? This is already we have seen. So fact 1. Fact 2 is that there exists two approximations to vertex cover. Now, okay. Now, what I'm going to say now again, it's a more like a future work, which is something that you will not need in this course, but per se. But one naturally asks, what happens to this 2? Can you improve it? Can you get 1 plus epsilon? Can you get 1.5?
Yes, sir, this is so here we are using multiple, but the
It is coming from these two endpoints of the
Yes,
age. Right?
yes, 2 coming for 2 endpoint of this age. Can we somehow do something? It seems like we can, right? There is a maximal. I mean, there's a lot of, as maybe Aniket was saying, there's a lot of clumsiness here. I mean, upper one was coming from the minimum, maximum vertex cover. So maybe we should be able to do some better analysis. But actually speaking, so this is what people had tried for a long time. And then sometime in the 1994 kind of stuff, it was proved that, okay, obtaining 2 minus epsilon approximation to vertex cover is NP complete. You might say, what is this thing? I mean, this is of course an optimization question. You have to change it to a
we can fix some vertex cover and just make it a problem.
yes. You can say that, okay, so I'm guaranteeing you that there is a vertex cover of size K. Go and find out a vertex cover of size.
If it
Yeah. So this is NP complete, which is basically, this is what is called as this area, this subject. So this is way harder than whatever we have proved till now. Okay. In fact, you will be surprised that this technique to prove this one requires harmonic analysis.
basically they would also be just trying to show this it is harder than some NP complete.
It is, but now what NP complete problems? Okay.
In
Now it is, yeah, so it's a long.
In theory, we can show it.
In technically, you can, in theory, you can come up with a very easy reduction. I mean, if there is a reduction from SAT, right? But that reduction is so complicated that we don't know the reduction. We know a series of reductions, and many of the reduction in middle goes into what we call as Fourier analysis of Boolean functions, basically harmonic analysis for finite groups. So this is what is known as, so this thing I kind of talked about earlier, this is called approximation algorithms. And this area is called approximation algorithms of finding an approximation to a problem that is NP complete, right? And this area, which is kind of just saying that how much, beyond how much you cannot approximate, this is called, I mean, it's almost as expected, inapproximate. Now, yeah, as I told you, this is beyond the scope of this lecture. In fact, it is beyond the scope of even the possibly an advanced course of algorithms. So this goes into, I mean, a complete course has to be dedicated to inapproximability.
Right. So I understand that the second one is an approximate to the BC problem. But why that thing is called approximate?
So this is like you cannot approximate beyond 2.
Okay,
so it is in approximation.
Okay.
I mean, you cannot approximate beyond 2. That's why it's called in approximation. Yeah. Okay, so that was about this vertex cover. I can talk more about vertex cover in other context also, but maybe yeah, we can talk about it later. But yeah, any other questions? Anything about these reductions and all that was done so far? Any doubt? I have asked the TAs to create a collection of problems on these reductions so that you guys can try out some of them. Okay. So I must say the reductions are a bit complicated. So it's not like it is.
Yes, especially in set, it's hard to.
Yeah, it is. And also it is one of those places where I cannot say that there is a particular method. Okay, it's not like, okay, you follow this technique and you'll get that. But if you do certain number of problems, you will get a hunch about what are the gadgets to be created, what kind of gadgets, like this a triangle gadget for the SAT, right? That's the kind of typical gadget that one creates.
For some problems, is it sometimes more convenient to prove that in order to prove NP completeness, is it sometimes more convenient to show that the problem is NP hard, if it is?
So that basically means that you are saying that if some problem you don't know it to be NP or not. We know. So okay, so there are many problems, many problems. Okay, which are beyond NP.
Yeah.
Okay, so they are harder than NP. So these problems are all of them are NP hard. What is NP hard? It is harder than any NP problem. Okay, at least as hard as any NP problem. So they are all NP hard problems. Okay. Now there are problems, even among those problems, okay, which are beyond NP. We don't know whether they are in, they are actually in NP. So sometimes it happens that we have managed to prove something like. Yeah. So so this is P, right? This is NP. Now NP complete is a set of problems. So okay, what is NP hard? NP hard is any problem that is harder than all other problems in NP. Okay, so you can think of if I have a problem out here,
At least as hard.
is at least as hard as NP. Hello? Yeah. Yeah, but somehow there are some problems here also, which is NP complete, which are also as hard as the rest of the NP problems.
Right.
Okay. Now it often happens that I have got a problem. Okay. So by the way, as I told you, there are huge, these are like onion layers. Okay. There's exponential, double exponential, triple exponential, goes on, and then finally we hit something called a decidability. Meaning these are the is there a finite algorithm? Okay. And many time it is not known to be whether there is a finite algorithm or not. Like, I mean, there is a kind of a huge system. Like, say you have a robot that you have made. Right. Now, question is that will that robot ever, do some particular job? Okay. We don't know. I mean, whether halting or whether it will ever. You make a robot walk, right? Or you have a small robot, and I'm like, will that robot ever come to that corner? How do I know that? So one option is to make it run. If it comes there, hello. হ্যাঁ আমি ক্লাস নিচ্ছি আপনি বেরিয়ে আছেন না না আমি ইয়েতেই আছি সিএমএ সেমিনার
Halting problem is another example.
Halting problem is a general example for tuning machines. Okay, but then there are problems that you can come up with a real problem that comes up in robotics and all. Many of the problems. Okay, in logic, in games. If you play a game, the question is that will that game ever halt? No, not in this course. Yeah, well, let's not go into tuning.
Yeah, fine. No, I'm saying that like if a program would halt or not, that's the halting problem.
That's the halting problem. Okay, now you don't know whether it's halt, right?
Yeah.
You'll run it.
Yeah.
If it halts, you know.
Yeah.
But if it doesn't halt, you don't know, right? So there is no finite time by which you can say that I will give you the answer, yes or no.
So in order to prove that some problem is NP complete, we may prove that it's in NP as well as in NP hard.
Right.
That's possible.
That's all.
Yeah. So is it sometimes more convenient or easier?
Many times that's what I'm saying. So maybe there's a problem here. you might find
reduction is showing
Yes.
is NP hard.
finding a reduction is showing that this is harder than all the problems in NP.
Right.
So it's harder than SAT.
Yeah.
But is that problem in NP? That reports are NP.
Right.
Yes.
For example, as I told you, right? A problem, the primes, okay? Set of all prime numbers. Is it in NP?
Yes, sir. Yes, sir. You told.
I told you it is, but it's not easy, right?
Yeah.
I mean, what is you have to convince me that so you have given me a prime number and you have convinced me that that's the prime number.
I was discussing with Aniket. He saw a paper around 2002.
Yes, 2002 is the famous paper, primes is in P. You can read that. Whoever is interested in that can read that paper.
I mean, is that something that we can read?
Yes, it's very much good. It's the equal of number theory, basic number theory, elementary number theory, what you call, no algebraic number theory or such things. Basic number theory, and you will be able to. Yeah. I mean, there is that paper, there is also some simplification of that paper that happened later on. Yeah, so primes in P is a very, I mean, outstanding piece of thing that we like. You might want to really look at. Primes. This is the name of the paper. Yeah, that really caused a massive. I mean, I was an undergrad student at the time in CMI, and when this came out, I mean, in less than 24 hours, I think everybody of us had a mail saying that okay, this has come out. It was groundbreaking. It was like, I mean, yeah, I mean, suddenly all the eyes of the world was in India. Like, wow.
So who did it?
Manindra Agarwal, Neeraj Kayal, and Nitin Saxena.
Oh, Indians.
Yeah.
Yes,
IIT company.
from IIT Kanpur. And two of them were undergrads. Two undergrad and one professor did it. It was possibly even now the biggest algorithms of complexity result that happened in this century. It was really big. It was like, yeah, I mean, yeah, there's a guy called Manindra Agarwal who was the main faculty at that time. He has gone on to become a celebrity in mathematics. Yeah, and the paper is really good, no doubt about it. And by the way, you should not say that this paper that was a suddenly that came out. There was a series of work that happened, huge series of work that happened, and I mean this was the culmination of it. There is another problem that is called a graph isomorphism problem. You know what is graph isomorphism? When is two graphs isomorphic?
Yeah, so we can.
Yes. The question is that is given two graphs are they isomorphic?
So we need to. So it's an NP or P. That's
Yeah. So it is known to be in NP. It's not hard to prove that it is NP. Okay. But we don't know whether it is NP, and we don't believe it is in NP complete. But we have still not managed to push it down to P.
Was this, I mean, a common belief that primes is in P before it was true?
Okay. So where is primes, right? So the first thing that primes happened was, so as I told you, that there is this P and P, right? There's also this opposite direction, right? Is the co-NP. Okay. Now primes was here. That is very easy to see. Why? What is co-NP? So co-NP is the set of all problems whose complement is in NP. So prime's complement is basically all the composites, right? Are composites in NP? Of course. If you give me a number and you claim that it is a composite number, how will you prove it?
We can just check from 2, 3.
I don't know. I am not so powerful to check. Again, the same thing will happen. 2, 3, 4, 5, 6. You've given me a number n. Then I have to check up to
finding the primes. That's
yeah. But you can give me a witness. Say that you have given me 91. I am a stupid person. I don't know what is 91. You have to convince me that the 91 is a composite number.
Oh yes, sir. So if we have the witness, like
Factorization.
Yeah.
You will just give me the factorization.
Okay, yeah, so that's possible. I mean, how would you
If
check that?
we have factorization, then we can just
Give the factorization to me.
we have a witness. If we have a witness, then we claim, so that's the basic checking of NP, right?
Right. But, I mean, how would we come what today?
Again, the person. So what is NP? What is NP? NP is those set of problems, right? Set of problems such that there exists a polytime witness, polysize witness, right?
Yes.
Witness for yes, or yes meaning
The answer.
when the answer is yes, there is a witness, and it is checkable, and I should write it, the correctness of the witness is checkable in polytime. Verifiable, right? It's verifiable in polytime, right? So there exists. There, you are the all-powerful person.
If you have a witness, then
Hello?
yeah, it's
Going-
yeah. So if we put the solution problem also, we should
No. আমার class চলছে আমার। কে
we
পরে
just
করছে?
need a solution. If we're able to verify that solution,
ঠিক আছে, ঠিক আছে, ঠিক।
in following that, then we can say that finding
Yeah.
the solution is the NP.
So think yourself to be an powerful person, all powerful. Okay, you don't have any restriction on how powerful you are. I am a polytime algorithm machine. I don't have a lot of time. Okay, so if you have to prove, say, it's called fact. Okay, fact is the set of all n such that n is composite. Okay. Now that means you have given me a number n. First of all, am I able to check whether that number is composite or not?
Yeah, so if we have a witness, then
If you give me a witness, then yes. Okay. First of all, if I can check it by myself, then that algorithm is fine. That is info P. Okay.
if we are able to find
If I can do it somehow, some other way, check, verify that number n is in this set. But if not, then you as a all-powerful machine or person is supposed to provide me witness. How will you come up with a witness? That's your job. That I'm not interested in.
Actually, I mean, I was confused at this part. That
Yes.
So how will we come out with the factorization?
Yes. So there exists. I'm not saying that there you can find one in polytime. All I'm saying is that the witness has to be polynomial size. Right. So in the case of factorization, fact, you give me an n and you are trying to convince me that that n is composite. Right? The witness that you will give me is that factorization. Okay, or any prime that divides that number. Okay, so here is the number 7, which divides 91. I'm going to check it. Now I am that much powerful to check whether 7 divides 91. I don't have power to find out that 7. But once you give me that number, I can check it. Okay. So who gives me the witness? That person is all powerful. So think of it exactly this way. It's like a Akbar Birbal thing. Akbar can verify, but solution has to come from Birbal, who is all powerful. Okay. So fact is therefore in NP. Okay. So since fact is in NP, so the primes is in co-NP. So the first thing that was done was that, can you prove primes is in NP also? If you can prove primes is in NP, then somehow you will be able to push primes from co-NP to here. It was done before.
Or to show, oh,
Yes, it was shown before, even before coming up with a polynomial algorithm.
what would be the witness in this case?
Yeah, so you have to do a little bit of literature survey for that. Okay, it requires some number theory ideas. It's basically kind of a combination of Fermat's little theorem and certain things like that, which will give you that. Okay. Now, still the problem was not in P. Then there is a concept of randomized algorithm. Okay, so randomized algorithm is an algorithm that uses coin tosses. Basically, it uses a random string, does some job, and with high probability,
Yes, sir.
manages to give you the right answer. Okay. Now, primes had a randomized algorithm that ran in polytime. It's called the Miller's algorithm, and that was a pretty well-known algorithm, and it was a very important algorithm. Okay. So, if you look at the story of primes, so first primes was in NP, ONP, primes in ONP, then primes was put in NP, which basically means that it's in NP intersection ONP. Then primes was put in, I will just add this name, but don't be off. It's called RP, which is basically randomized algorithm. Randomized polytime algorithm. And finally, prime was in. This was the step that was done. And every step, of course, in some sense, took some
So
20,
RP is
30
where
years.
in the diagram. RP is where.
Okay, RP is where RP comes up slightly off. But I don't know really going to it. RP, of course, contains P. Okay, but it's not necessarily contained in NP. It's somewhat like this. Okay. Yeah.
So we also did like so suppose we want to find the minimum distance between two vertices in a graph. So
Yes.
we can just do at every vertex do a randomized thing and just run it again and again.
That also you can do. Okay.
That is RP or
So question is that if you do a find the minimum distance between 2 points in a graph by using randomness, by random walk, means that you will find a path, but with very low probability, it will be the minimum path.
so there might be a case where the probability is quite less, but the paths would be minimum.
Yes, but that's not good enough for us. So RP is the case where you find the correct answer with this is
high,
called
high probability.
not high but bounded probability. Reasonable is a constant probability. Okay.
So at some point it is stagnant. I mean,
Something like, let me give you a completely not a very easy thing. But if I ask you to give me an n-digit prime number, can you give me?
n-digit prime.
Yes, I give you an n. I ask you, give me an n-digit prime number. It's very difficult. Now, this problem is, by the way, one of the most important problems because, as I told you kind of briefly, that the whole world of cryptography, which includes everything from what we are talking on the phone to media to military things and all, right? They depend on what is called an RSA code, which is basically based on obtaining large prime numbers. Okay.
Yeah.
No, I mean, you take two large prime numbers, multiply them, and that is the number that we kind of push it. Okay. So, but we need this large prime number. How will you get one? Any idea from the people who are attending online? How can you produce a large prime number?
There are certain forms that we have studied. I mean, we have studied this.
There are certain forms of primes.
Like
So like 2 to the power n minus 1.
2 to the power n minus 1, but that also is not fully prime.
It needs to be, the n should be prime something.
And then I don't think it is known to be prime.
yeah, it's not known. It's not. We have
It
to-
is conjectured to be prime or something.
It's some prime.
Huh?
Some prime.
So they-
Mersenne prime also, yeah, there is some kind of Mersenne primes also. There is the infinite number of Mersenne primes,
There have-
but it's not known that which of them are primes. Okay, there are infinite number of Mersenne primes.
Yeah, which of them are primes?
Yeah.
So in fact, does there exist any known result that which gives us arbitrarily
No,
large?
No,
so there are
not- no.
algorithms which
But we don't need such a thing. We need an algorithm.
Right.
Think about it. You know it. You know these all the basic ingredients, believe me.
Sir, what if we were to multiply some primes and add one or something like that?
Okay, good. Very good point that you showed. So that is how we end up proving that our primes are infinite, right? We multiply the primes plus 1. But that doesn't happen. That doesn't happen, meaning that you
Yeah,
first
yeah,
take the
yeah,
first.
yeah. That's the
Yeah.
contradiction in this statement. All the primes. No.
I mean, first of all, yeah, you have to take all the primes up to some number. Okay.
But
Even then you do it, you will not get a prime.
that's a contradiction. So if you're taking all the primes, so you're first assuming that there is a certain set, a finite set. So that gives a contradiction. Then you get that there is no finite set. So there is infinite prime. So that's a proof. Yeah.
Yeah.
We're not.
Yeah, but yeah, exactly. That's the use for a contradiction. If the number of primes are finite, then multiplying all the primes plus 1 will be a prime.
Will be a prime.
But that is not a way to generate a prime.
that is not true. I mean, because we cannot multiply all the primes. Right?
Yeah,
Because
actually, I
we
forgot
can-
exactly the numbers, but I think there's some very low number, like first 7 numbers, 7 primes or something, multiply them and add 1, you get a known prime.
Oh,
So they've got to come up with some. Okay, if I give you a number,
yes, sir.
if I give you a number, can you check whether it's the prime or not?
Like, so the basic algorithm that we thought was exponential time.
Yeah,
exponential-
but okay, you know that there is a result, right? For
Yes.
primes is in P.
Yes, sir.
So there exists a polytime algorithm to check.
Yes, sir.
So if I give you a number,
Then we can,
you can check whether it's the number is a prime or not.
yes.
Excellent. Now,
Okay, so there are some things like gaps in prime. I'm not sure.
you don't want the gaps in primes. You want to require a.
No, sir. If we are, so suppose I want the n-digit prime,
Yes, you want the in-digit prime, then what will you do?
then I start with like 10 to the power and just to try to check.
Okay, let me ask you a completely different thing. Okay, if I give you a box full of balls, okay, and out of there is 10,000 different balls there. All of them are white, but except for 100 of them which are black.
Yes, sir.
I ask you to go and find a black ball. How will you do?
So it will be, I guess, we
Will you kindly repeat the question?
Yeah. So you have a box full of balls. Okay, 1,000 balls, out of which say 900 of them are white and 100 of them are black. I ask you to go and find or produce a black ball. What will you do?
Sir, I will find 10 people who are willing to help me and then just give them 1,000 balls each and give them the separate problems.
You will put 1,000 people, and yeah, that's a good thing. That's the. But I mean, just for once, think that you are from ISI. Come on.
there was, so I guess we can check certain forms that are known. So
You
like-
go to an industry and they say that they are producing light bulbs.
Okay, so
Okay, and you know that 10% of the light bulbs are wrong, but you have to give them a proof.
that tend to- we
So
should
take
take
a sample of-
sample
You take a
of-
sample. That's exactly you do. You pick a random element. If you pick a random element, what happens? The probability of getting say in a case of box, probability of getting a black ball is 1/10. Repeat it 10 times. Repeat it. And by Charnow bound or concentration lemma, you will know that by the time you chip, you repeat the whole process 12 times, with almost certain probability, you should have got a black hole by then. Right? That's it. Now, what do we do with primes?
Okay, so we don't know how the primes are spread. So
Do you not know? Think.
there was some like until n is log of n number of prime number.
Yes. There is something called a prime number theorem. What is that? Prime number theorem says that
It says finding the log is something, right?
yes, so number of primes less than or equal to n. Okay, this is the number of primes less than or equal to n is almost, now this is actually seen, this is asymptotic notation. Is actually n by log n. So now what will you do? You know this number, right? So it is exactly like if I take a random number, a random n-digit number. Okay? What is the probability that that's the prime?
We replace it in by 10 to the power minus 1.
It will be.
No.
So if n is equals to 2 to the power k, right? I mean, so I'm looking for a k bit number or k digit number. Okay, let's look at k bit number, k digit number. Right? Log of k is k, some constant k, right? Order k.
Yes.
Log of this. So I pick a random number with probability 1 by k, around 1 by k.
So
I am getting a number which is prime. I check which is the prime using the prime number, this primes is in P algorithm. If not, throw it away, repeat it.
Okay.
How many times do you have to repeat it?
So 1 minus 1 by k to the power n would be the number.
Could you please repeat this?
Okay, exactly. Let's go back to again. Okay. You are now, you can think of them that the total number of is a box of numbers.
Some are prime, some are composite.
Some number, some are composite. Okay. Probability that a number is composite, sorry, is prime is 1 by log n. Then how many times do you have to repeat to obtain a prime?
Log n time.
On expectation log n times. If you do, yeah, on expectation, if you run log n times this experiment. So go pick a random number.
We shall get a prime with probability 1, like something like
It will not get prime with probability 1.
No,
No, that doesn't happen. Come on, expected value.
Expected. Yeah, sorry.
Yeah. So,
Expected number of operation that you have to do is log n to get a prime. Now you want to, if you apply this, if you want to, now if you apply this concentration bounds, something that I had kind of talked about maybe in the beginning. If not, I'm the Charnov bound, Chebyshev bound,
yes, sir.
Markov bound. Okay. Yeah. So you can prove that if you make something like 2 log n number of samples, there is almost high probability, meaning 1 minus small o of 1 probability, you are getting a prime.
exponential.
Now, can I have it? Why will it be exponential? How many samples are you taking? Let's say. Okay, let's do the calculation. Okay, I want a prime of k digit. Right? So, what is the number of numbers that are there of k digits? It is 10 to the power k. Right? I mean, let's assume that the first one is not 0. So then it's around 10 to the power k, 10 to the k minus 1. Doesn't matter. Okay. So the n is 10 to the power k. So that means the number of primes that I have to choose. Okay. So if I pick, okay, so Okay, I should not write pick. So probability.
Hello?
Or,
Hello?
hello. Yeah, can you see?
Sir,
Can you are
the picture quality suddenly became very bad. The video quality.
even now?
So it's not so clear. I don't know about others, but for me it's not so clear.
What about others? Aniket?
In the middle it went back.
Sir, I'm
but now
facing
it's
some
okay.
connection issue.
Okay. This is exactly the reason why I was not configured to have this thing somewhere.
In the
Is it
middle it was
true?
showing the bandwidth is low, but now it is okay.
Now it's okay?
Yes, in the middle it was saying that your network's bandwidth was low. So the video quality dropped.
Okay, now is it fine, right?
Yes, now it is fine.
Okay, so let me just still continue a little bit here. Maybe I will just use the top one. Okay, so that might be slightly better for you guys. Yeah. So probability that a random number is a prime. Okay, what is this? So random number meaning random k-digit number. This is by this thing, it is 1 by k. I mean actually something, some constant times k, right? Maybe 5k or something like that, right? Fine. So if I pick a random number and check, right? Yes. I can do it. Okay, good. Now, how much time does it take to check if a number is prime or not? Polynomial in what? Polynomial in k. Right. So time to check if a number is prime. This is poly in k. Right? Okay, good. So I pick a random number, check if it is a prime or not. If not, I repeat it. Number of repetitions equal repetitions needed with high probability. It is around order of k.
So order of k square.
So order of k square. So total runtime is order of k square, which is polynomial in, and this polynomial in k. Let's put it this way. Correct. So see, this is kind of not a very good example, but some example of how a randomness helps.
This is also like approximation algorithm. Or
This is not an approximation algorithm. We are not. So approximation algorithm is for an optimization problem where you have to output something and then you approximate it.
This doesn't necessarily give answers.
This is with high probability. I will be saying that okay, this is giving a difference. Okay, so this is a randomized algorithm. And there are quite a lot of randomized algorithms. It's a pretty interesting if you start thinking of there. So algorithms as such is so whatever we are going to do in this course or whatever we have done or something, there are very basic stuff. Okay. Of course, quite a lot of things there. However, I will possibly stop today's class using one example, something to think about. Again, just a fun thing. This is called online algorithm. Say you are a thief. Okay. And imagine that you got stuck in a jail. Okay. So you have a huge wall around it. Right? But you know that somewhere down the line here, there is a hole through which you can escape. Okay? But this boundary wall is massive. You can almost think of it to be infinity. Okay. But you have somehow reached here. Now the problem is that you have somehow reached to this wall. You can walk along the wall undetected. You don't know which direction to walk. Okay.
So we are not allowed to walk. So we can, if we reach the side, we can go back, right? We can
No.
go any direction, or just
You can
along?
just go this way or this way, only along.
Okay.
Right? You can just walk in either direction along the wall.
Okay.
Now, how will you come up find this hole? See, sometimes you know that. See, I mean, if I am here,
What
the minimum distance is d, let's say.
Yes, sir.
So ideally, you don't want to walk too much more than d.
Yes, sir.
Right? That is the best. D is the best. The other side is almost infinity.
Okay.
How can you come? Can you come up with an algorithm that will help you to find this hole?
Okay, so
what information and what else?
Do nothing else.
so basically, what we are supposed to do, we are supposed to go one side, and we have to choose a stopping time. Right?
Yes, and then
We have to change
yeah,
direction.
good.
and-
Think. Yeah, you have got it right. Let's the other two things. Yeah. So this is what is called online algorithm, where you don't know what you are trying to optimize. I mean, you are trying to.
D is also not known.
D is not known to you, right? So D is not known to you. So you want to compare with yourself with D.
Yes.
Okay. So you want to compare yourself with an optimum solution, which is not known to you.
And so this is not a NP.
No, this is not about the NP and P kind of
This is
stuff.
just a finding.
This is what are called as online algorithms. Okay, online algorithms because you don't know what is coming, basically.
Okay.
I mean, so algorithm is not just one kind.
Okay.
That's what I'm trying to say. There's algorithms of various kinds. Algorithms is a way of finding it, something. Okay. And by the way, you will learn a little bit of this one possibly in your optimization course if you are taking the MStat course or something, where you do linear optimization or online or convex optimization, and you do. I don't know, maybe these are some words that you can just learn later on, the gradient descent and all this kind of stuff. Yes, so these are basically, toy forms of those things. Okay, think about it. Okay, any other questions about this course? I mean, I can keep on motivating you guys on algorithms, but that will not help possibly.
Sir, I mean, will there be a total of 7 assignments?
Something like that. I have not yet thought about it. Yeah. Why?
No.
Time.
Oh, time is not much time. How much? Then maybe. So there has been 4 assignments. Okay, we'll see. Don't worry about it.
You consider the last day as one assignment?
3 more weeks.
Let's see. You submitted?
Yeah, I did, but
That's fine. As long as you submit, it's okay. Okay, so any other questions from your end?
oh, sir, exam marks.
The marks is I will release it tonight. Yeah, it's more or less done. I release all of your exam marks at one time. Okay. Yeah.
And our next sessions will going to be online.
No, let's do it online only. I mean, I know that I'm also so happy to see some of you at least face to face. But I mean, this kind of problems with the connections and all those things do exist.
Connectivity issues can be resolved if you go like in this.
No, but it's problem is not about connectivity here. I mean, like somewhere, I mean, like I say, all of the internet connections are. See, one thing is that let us do this thing, okay? Let us meet here for this, like this tutorials. Okay, if you have any doubts, questions, that will be better to face, and rest we will try to meet. And also, my office is right down the corridor, so if you guys anytime can drop by my office.
Okay, so in case you can have this class on Tuesday, that would be a little bit better because we have an offline class from morning session.
Okay.
Morning session on Tuesdays, and your class is in the next session.
Okay.
So on Friday we have a morning session is offline. The next session is again online.
Okay. Okay. So maybe let's try to have this next class online. offline. On Tuesday, let us have it offline. Okay. Here only. Okay.
So I was facing a bit problem in like finding the reductions and such.
Yeah. So you have to do some examples. Okay.
So,
I would suggest that you do examples and then
so from that climber.
Climber.org. Okay. Yeah. I mean, Climber, CLR, both of them are fine. I mean, any of them. Any of the books are good enough. Okay. So then I will stop the class for now. Okay. See you.
So you are here till
I am so every day. I am here till around 4 o'clock, say usually, mostly. Yeah, okay. But if you, yeah, but I'll be, I mean, I'm sure you will be able to find me. Okay. Okay, so maybe I should just ask you. So people who attended this class online. Hello, Aniket, Abhi, Chandramouli. Yeah,
Yes,
so
sir.
are you fine with this course or this class?
No, sir. I personally not.
You personally didn't enjoy.
No, sir. The previous online lectures that you used to write,
Right.
that was better. Here, the main problem is that the screen is not much clearer. So,
Okay.
and also there are some issues.
Okay. Okay. So screen in the other class is fine, is it?
No, sir. In online class also we face this issue.
yeah,
The,
today
the
It was fine. Actually.
I mean for us it was
Yeah, for others, for the online people.
Okay.
So actually, we got a new rule with it. So I guess for the online people, even that is fine. I'm not sure.
Chandramouli was not even there.
actually today I did not attend the parametric inference class, so I don't know.
Yeah, so today was
Okay, so what about Aniket? Aniket, are you there? Maybe Aniket has some connectivity issues, that's what he was saying. Okay. So Ritobrata Karmakar, are you there?
Sir, this is Aniket.
Yes. Yeah. Okay. One of you speak. Okay, Aniket, you can speak. Both of you have muted yourself.
Sir, it was fine for the first 45 minutes or so, and then there were some problems.
Today? Yeah. This class? Sorry, this class, Aniket, you mean?
Yes, sir.
Okay. Okay.
Sir, what about the last class?
So your friends are asking, what about the last class today in parametric inference?
Sir, generally there's not much of an issue. It's just it's better for the online people if the class is online, but it's not that big an issue, at least for me.
Okay, so I can do one other thing. Okay. That will be
you said
useful.
some sessions you can arrange and Friday session, I guess.
Yeah, that would be, I think if you can at least meet up sometime, I mean Friday sessions or something like that, and then the rest of them let's continue online as if we are doing it. Okay. Okay, so in that case, let's do it like only. Let's continue online and do offline only the tutorials or some sessions like that. Okay, good. So see you guys. We'll stop it.